We just got done with our forces unit, where we added up all the forces on an object and examined the effect on motion. And one thing about the forces in that unit, you probably noticed that they were orderly. They were usually constant or easily predictable. They were something that was easy to observe, either with our eyes or using tracker. So, what do you do when a force is non-constant and non-reproducible and hard to pay attention to? Is there any way you can find out about motion? It turns out there is. And I'm going to use this apparatus here to demonstrate how. There's a class of motion called an explosion. It basically just means you have one object, it blows apart into two. We'll do a fairly simplified explosion here. I've got two carts. Between them there's a spring-loaded plunger, and when I release that plunger, we get motion. And not surprisingly, these two carts went about the same distance. Not exactly the same, because this one seems to have a little bit more friction acting on it. But we expect them to go about the same because they were fairly identical. Let's see if we can get some information on motion from the different carts. Now we know a lot about motion. We've got these equations. Can we use them here? Well, one thing you got to remember is that this parabolic position versus time graph, it comes from having a velocity that increases at a constant rate, a linear velocity time graph. That happens if you have an acceleration that's always the same. Like when we drop something here on Earth, the acceleration is always minus 9.8. You don't get these two equations if you don't have a constant acceleration. Do we have one here? For the purposes of this discussion, let's call the card on the left cart 1. I'll put it in orange. We'll call the card on the right cart 2, and I'll put it in yellow. What made them go? A compressed spring. Because it was compressed, it started out with a large value. But as you let a spring grow, it starts to stretch out. It starts to push less. So as the two carts moved away from each other, the force began to drop. And at some point, the spring got totally uncompressed, and it went to 0. So we have a force that's decreasing. That's a problem for using these equations, because we know sigma F equals ma. Force is proportional to acceleration. So if we have a decreasing force, we have a decreasing acceleration. And that's not this. So we can't actually use those equations to describe what's going on here. Furthermore, we don't even know if this is linear. With springs, actually, it should be, which is something you'll study in a college physics class. But, you know, these are old springs. There's junk inside those carts. Maybe it was catching on something. This could be some crazy, weird graph. We know it's decreasing, but it may not be linear. So how can we get any information about motion? Well, this graph can help us. It's a force versus time graph. The area under the curve on a force-time graph is impulse. And the impulse of this graph is cart 2's final momentum, m2 v2f, minus cart 2's original momentum, m2 v2 o. So this relates the area under this curve to motion. But again, what's the area under this curve? Turns out we don't have to care, because of another trick we can use using Newton's third law. For every action, there's an equal and opposite reaction. And that means that as cart 2 got pushed, so did cart 1, but in the opposite direction. And that's true at every single instant. However hard cart 2 was pushing cart 1 was pushing that back. And that means that cart 1's force versus time graph started out with a large negative force and decreased over the same time period. Here's the cool thing. Because those two areas are equal, we can set them equal to each other. And actually get rid of any dependence on force and time at all. Let me show you how. We have the impulse on cart 1. It's opposite the impulse on cart 2, so I'm going to put a negative sign. Just sub in the m's and the v's. So negative minus m1v10 equals m2v2f minus m2v2l. So I'm just going to do the algebra real quick. I'm going to try to rearrange this to give us some information. I'm going to try to put all our original momentums over here, and all our final momentum over here. And we'll see if that gives us any useful information. So I'll start by distributing this minus sign. Now I'm going to add over m1v1f, so it's over on the final side. I'm going to add over m2v2o, so it's on the original side. So if I do that, I get some massive cancellation. And I'm left with m1v10 plus m2v2o is m1v1f plus m2v2f. So I'm left with all of my original momentums added together. So we could just call that sigma mvo. And I'm left with all my final momentums added together. You can call that sigma mvf. And what that tells us is that in an explosion where two pieces get exactly the same force at exactly the same time, all we have to do is keep track of the original momentums that those two carts had. Keep track of the final momentums. They will be equal to each other. So this directly relates the velocities of the two carts. Let's try to use our new equation to explain why the two carts left with about the same velocity. So if all the original momentum equals all the final momentum, think about what our original momentum was. We had a mass, but our original velocity was 0. And that was true for both carts. So we ended up having no original momentum. And that had to be equal to our final momentum, m1v1f plus m2v2f. So 0 equals m1v1f plus m2v2f. So I'm going to subtract m2v2f over to this side. M1v1f's on the other. Since our carts had exactly the same mass, this guaranteed that they had the same velocity, but in opposite directions. We don't really have to write m1 and m2 since they were the same. So we had minus mvf equals So that explains why we had the same velocity for the two carts originally. But check out what happens when I reset it. And we'll have part of this guy, we'll transfer its mass to the other one. The motion actually now becomes pretty dramatically different between the two carts. That one goes a lot farther. So is there any way we could have predicted how much farther it went? So why in this case did one cart have so much less velocity than the other one? Well, let's go back to the conservation of momentum equation from before. Just like before, both carts were at rest, so there was no momentum in either original case. And that had to be equal to M1, which I'm drawing bigger, V1F plus M2 V2F. Why did I switch how I drew the velocities? I drew them much bigger. Well, if we go back to this equation, if these two terms have to be equal, if we had a small mass here, we must have had a big velocity. If we had a big mass here, then to balance out, we must have had a small velocity. That's the only way these two can be equal. So the fact that the lighter one went much farther is signified by the fact that it started with a larger original velocity, which was because of the mass difference.